Hi, I'm Francesc Campoy, and this is Just for Funk. Welcome to episode number 18 of Just for Funk. Today we're going to cover something that is a little bit special. Rather than building a project or reviewing some code, we're going to try to explain a concept. Since Go 1.9 was released last Thursday, August 24th, today we're going to be reviewing the most important change to the language in that release, which is type aliases. Now, type aliases are actually very simple to understand. There's nothing really that complicated about the concept of an alias. It is what it really implies, just an alias. But it is actually not that clear why we have them, or even when to use them. So that's what I try to explain today. We're going to try to first understand how types work in Go, and then figure out why type aliases are a thing. Does that sound fun? Let's get started. Let's start by understanding types, and let's start specifically by understanding the type keyword applied to concrete types. Concrete types in Go are those types that are not abstract, and the only abstract types we have are interfaces. So concrete types are all of the other ones. Ints, floats, structs, channels, functions, all of those are concrete types. Let's think about those first. Okay, so let's say that I define a temperature type Celsius, which is float64. Now, I have this type. This is a new type that has the same layer in memory as float64. And we can attach methods to it. So we can say func c Celsius. When we print it, we want to actually say sprintf. It's going to do point to f, and then a space, and then the c. So now if I use that, I can do c is Celsius of 10 degrees. And if I print c, and I forgot a c there. So if I run this now, go, we'll say 10 Celsius. Cool. So we have a new type, Celsius, that has the same layer in memory as float64. And that is why we can do this conversion from float64 to Celsius. And also we attach a method string in order to control how we print it. Cool. Let's now add one more type. And I'm going to say that that type is going to be temperature. And since I'm European, for me, temperature is always Celsius. Fahrenheit does not make any sense to me, or in general, really. But that's a different conversation. So I'm going to define a new type temperature, which is simply Celsius. I'm just going to say, OK, the type temperature is the same thing as Celsius. They're basically the same thing. Cool. So now I should be able to say T is a temperature of Celsius. And then print it. And this should print exactly the same thing, right? It should print 10 Celsius, 10 Celsius. But no, it doesn't. Why? Well, because the type keyword, what it does is it defines a new type that has exactly the same memory layout as whatever you put on the other side. So in this case, type Celsius has the same memory layout as float64. Type temperature has the same memory layout as Celsius, which is the same memory layout as float64. So that's why we can use a 10.0 to be more specific. 10.0, which is a float64, can be used as Celsius, and a Celsius can be used as a temperature. Also, you could use simply here a float64 because it's a Celsius, and Celsius is temperature. So basically, all of those types share exactly the same memory layout, so we can do conversions across them. But the methods are not passed. So here, the method string is attached to the type Celsius, not to the type temperature. So how could we make this work if what we want to keep is the methods? Well, you could think about, in other languages, you could do inheritance. But Go does not have inheritance. Instead, what we have is we have composition, and a specific case of composition where we expose all of the methods of the type composed into the composer type, which we call struct embedding. And that looks simply like this. It's basically a field that doesn't have any name, just a type. So the name of the field will be the name of the type, if you want to use it. Now the difference is that when we create a temperature, now we cannot simply go from 15.0, which is a float 64, or from C, which is a Celsius, to temperature, because now temperature has a field which is a Celsius, right? So we actually broke that thing of having the same memory layout. So instead what we do is we're creating a temperature that has a C. That's why we're passing from the parentheses of the type conversion to the curly brackets of struct literals. And now this should work. Cool. Okay, so for concrete types, either we have something that has the same memory layout, so we can do conversions from A to B, or we have something that has the same methods, or even more technically, because you could attach more methods to temperature if you wanted. So basically, it keeps all of the methods that the embedded type had, right? And that's it. There's no extra things. You cannot create a type that has the same memory layout and methods as a previous type. That is where type aliases come in. But we'll see that later. It is also worth mentioning one little detail that will help us understand one more thing that type aliases are useful for, which is the fact that type conversions, like this 10 to Celsius, or the one that we had before, the temperature, the Celsius to temperature, which we don't have anymore, are only doable explicitly unless one of the types is unnamed. Now, let's understand what I mean by that. So, if I want to, let's have another type, which is another temp, which is a struct, and has Celsius. These two here have exactly the same memory layout. Actually, we could even simply do temperature. And I could try to create something like this, where I'm creating another temperature given the value of T. And this will not work, is saying you're trying to use another temperature, a value of another temperature as a type temperature, which is not, so you cannot do that. But you could do that type conversion there. This type conversion, explicit type conversion, is only necessary because temperature and another temperature have explicit names. But if you did something like this, where you're actually you're giving the value of an empty, there you go. You're passing the value of a type that has no name. This doesn't require to have explicit name, explicit conversion. And this seems like a little detail, but it is actually important because it means that naming things has an impact on the code you can write. Okay, so in order to understand this a little bit better, let me write some more code, some new code here. So let's imagine that we have a type function, type func, which is an empty func that doesn't receive any parameters, doesn't return anything. We call that a func, and we define a new function, a new function run of that will simply run the function. So if we had a function hello that prints hello, we could do run of hello. And why would we even have this type function here? For documentation purposes, basically. We could say func is a very useful thing to document. And there's packages that do this, by the way. Func, there you go. Okay, so we have all of this, and this works. And this works because the type of hello is not named. The type of hello is actually, so if we print that, and you can print the type of something with this ampersand capital T. So if we print this, you will see that the type is a function that doesn't receive anything, doesn't return anything. That is not a name type. That is just the description of the type itself. So we can do the conversion from that to func quite easily without having to explicitly do the conversion. Now let's imagine that we have another func, which is exactly the same thing. Actually, it's so much the same thing that we're going to call it like this. And let's not make that exported. And somehow we have another func. So we have that f, which is hello. And now, so we're doing a conversion from that unnamed type value, which is hello, to a name type. Now it's named another func. And if we print it, we should see that this does not compile. And I'll explain why in a second. But it prints main dot another func. So now it is not empty func. It's not that func anymore. It is now has a name, which is another func of the package main. So if we try to just run this like this, it will not work anymore, right? And everything that we've done is simply do that extra conversion. The value is the same. We just change the type. And it doesn't work anymore because it says you cannot use the type func, capital F func, as a type another func, because they're not the same type. They do have the same memory layout, but they are different types, and they both name, so you need to do func. And that will make it work, right? And that seems like a tiny thing, but we will understand later why this is actually kind of important and how type aliases solve the problem. Okay, now we kind of understand how concrete types work, right? You have concrete types, you do type whatever, whatever, and what you're doing is defining a new type with the same memory layout of whatever is on the other side, but none of the methods. When two types have the same memory layout, you can do conversion from A to B, and that conversion needs to be explicit unless one of those types is unnamed, such as the example we had a minute ago. Cool. What about abstract types, interfaces? So for interfaces, basically, if I define a new stringer that is simply fun.stringer, so we're using the same one, which, by the way, is an interface with one method string that returns a string. If I have two different values, one of type, I'm going to call it my string ms for my stringer, and another stringer, which is fun.stringer, if we print ms equals s, we will actually get true. Because these types, even though they're differently named, for interfaces, what counts is that the two types are identical. And identical for interfaces means they have exactly the same methods. So in this case, both have exactly the same methods. So we don't have that problem of having conversions. Also, so if I do ms equals s or s equal ms, these two also work without having to do a concrete, explicit conversion, because when we do this, what we're saying is this will work as long as s has all of the methods required by ms, and here will work as long as ms has all of the methods required by s, which is true in this case because we have the same interface. We could also do interface like this, which is kind of similar to struct embedding, but for interfaces, what it means is that we're getting all of the methods defined by stringer and putting them in this stringer, but we could add more. So in this case, one of the conversions will fail because s does not have all of the methods of ms anymore. But if we just have this method, everything works. We could even just do basically like the copy paste and have the two stringer interfaces be exactly the same, even though they do not depend on them, and everything still works. Because the comparison here is not on memory layout or anything like that. It's just on the methods themselves. So with interfaces, it seems like it should be easier to move them around because everything is pretty much the same. and still type aliases are very important for these. So I guess we're ready to understand what type aliases are. Let's start with a very simple example. So if we go back to the example we had before with the temperatures and the Celsius and stuff, something we can do is, so we said that either we make something that is convertible from temperatures to Celsius, or we have something where temperature keeps all of the methods from Celsius. In this example, we use struct embedding. Therefore, we keep the same methods. So we'll print as expected, but we can do conversions from temperatures to Celsius. In this case, we can do the conversion, but we're not keeping the methods, so the 10 does not print as before. Well, if we wanted to define a new type temperature that not also had the same memory layout as Celsius, as in this case, but also it kept all of the methods, as in the previous case, something we can do is use a type alias. And a type alias is something as simple as an equal. That's it. Now, when we do this, and if we print this, now we'll print 10.0 again, as we wanted before. And what is this really doing? Now, all of a sudden, we have both the methods and the memory layout. And the important thing to understand is that everything we've done is just give a new name to the same type. We have not defined a new type. So this is not even necessary anymore, because temperature and Celsius are exactly the same type, to the point that if we print the type of, let's print the type of Celsius and the type of temperature, you might expect to see Celsius first and then temperature. But you'd be wrong. It will print Celsius both times. Why? Because temperature is not a new type. Temperature is an alias to an existing type. So you could even imagine as something that is basically a macro that will be replaced by something. So everywhere where you see temperature will be converted into Celsius. Now, this is interesting because it means that all of a sudden we can do things that before we were not able to. So if we go back to the example with the functions, here, in order to be able to document our type function, we had to give out our ease of usage, forcing people to convert to func specifically if their functions were of a name type. Now, we can actually drop that requirement by, instead of using a normal type, a new type, we just use a type alias. Now, the type alias func, which is the one we're using here, it does not require to do the explicit conversion, because this type, even though we gave it a name, it is actually just an alias, and the type still does not have a name. So if we drop this, this will still work. And if we printed the type of run itself, you would see that is a function that receives a function. It's not a function that receives that capital F func. It's a function that receives a function as a name type. So that's why we can get any type named or a name, and as long as they match the memory layout, we can use it as our parameter. So that is pretty cool. But this is still not why type aliases exist. Let's see why. Okay, so for this last part, I'm going to talk about refactoring. And refactoring is the main reason why we have type aliases. So I'm going to be refactoring things by moving them from package A to package B. I'm going to call those packages old and new, so it is easier to remember in what direction I'm moving things around. And then we'll have a main.go, which is the one using those packages. So let's create old. Let's create new. Outside, please. And we're going to have new.go, which for now is going to be completely empty. Package new. And package old, that's going to be package old. And in this case, we're going to have, let's say we have a constant, OK, which is a Boolean, which is true. okay is okay. Okay. So in my main function, I can use old.ok. I can print old.ok, and this should work. It complains because I have too many. Actually, let me move the examples we wrote before out of the way, so this doesn't complain anymore. Okay, so go run main.go. So it prints true. Why true? Well, because old okay is true. Cool. What if we wanted to move it from old to new? So for any refactoring, we need to follow 3 steps that should be completely independent, and in between those steps, everything should still compile. This is because if new, old, and main were in different repositories, and let's imagine you had like continuous integration, you do not want to break the build in order to do this change. So to be able to do this, we're gonna first change new. So we're gonna add the OK constant to new, then we're gonna change our main, and then we're gonna drop the definition from old. And this is what we're gonna be doing for every single kind of refactoring. So just going to copy paste. So now we have the same constant both in old and new, and simply we change the name here, and that's it. Now this program does exactly the same, and no matter how we were using that variable, that constant before, we can still use it exactly the same way, because 2 constants of the same value are exactly the same no matter what. So easy. Now this is still working. Let's run it. Cool. And we can finally, once all of the usages of old.ok are gone, we can drop old.go, and everything still compiles, everything runs, we are all happy. Cool. This change might take months if you're doing it over an open source project, but this allows us to actually make this change happen. Cool. What about functions? Let's say we have a function hello that prints hello, and hello says hello. I'm very original with documentation. And now we want to, let's drop this. No, let's not drop it. Okay, so now I want to do old.hello. Right, so when I run it, this prints hello. Cool, so this is a function. How do we do it so we can move this old to new? We could do copy paste, but there's a little bit of a concern with the fact that, well, then we're duplicating the code, and I don't want to do this because the code might be very complex. So you could say, well, do not worry, you can do var hello equals all.hello. And this works, but I'm not very happy with this because now it means that from here I could do new.hello equals nil. And I really don't want people to be able to do that, right? We were not able to do it before. Why would we be able to do it now? So instead, what you can do is the new hello, it's going to simply call the old hello. That's it. Passing all the parameters, returning all the values, whatever. In this case, there's nothing like that, so it's pretty simple. So now you cannot do this new.hello equals nil anymore, but you can still call new.hello. So we added the new function. We changed everything that used the old one to use the new one, and then we drop the old one. Cool. Now let's go with variables. Actually, let's keep variables. Variables are pretty much like constants, other than for the fact that if you have pointers to them, this will not really work. Now, normally you should not be sharing pointers to public variables. That is kind of a weird thing to do. In general, what you do is you use them as errors, stuff like that. Otherwise, global variables in packages that are exported are pretty rare. And if you're doing that, show me the code. I'll be interested in seeing if it actually makes sense or not. And if not, it'd be a good code review episode. So let's move into types, which is the main topic of the episode. Okay, so for my last example, I'm going to define a new type and try to move it from old to new. But on top of that, I will also have one extra package which will be a utils package, and we'll see why. So we have our new, old, and utils. And in old, I'm going to define a type person, which is a struct. And let's say that has an age, which is an integer, and name, which is a string. And also it has, let's say that it has a method, string, that returns printf is t. So p.name, p.age, cool. A person is a person. Okay, so we have this package. And then we have the utils package, utils.go. By the way, both utils, old, and new are awful package names. Do not use them, just here for the example. And in package utils, we're going to have a function that says is major of a person and returns a boolean, returns p is p.age, so old.person, p.age is bigger than 18, because that's what major age is. Is major returns whether a given person is old enough. Okay, so now in main, we're going to be using both of those packages. So we're going to have a p, which is old person. Let's say it's me, Francesc. By the way, that's how you spell it. I've got a bunch of people sending me messages, and they never spell my name correctly. It's not that hard. And I am 34, I think. Also, is this the right order? No, it is not. It's the other right order. Okay. So actually, let's use this to make sure it's actually correct. And I'm gonna do util is major of p. P.name is major. And I'm gonna print that. Utils.is major. Okay. So now if I run this program, it says Francesc is major. True, indeed, I am major. Okay. Let's try now to move move person from old to new. So what we need to do first is we need to make something in new that will be compatible, fungible, exactly the same, and replaceable for any API that is in new that is exactly the same as in old.person. So we could do type person is old.person. Now if we do this, and we migrate here, we say, oh, we're going to use the new person. This does not work. And it doesn't work because is major receives a new person, right? It receives an old person, but now it's receiving a new person, so that does not compile. So that is a problem. We cannot do this. So what if instead we migrate first utils and we say, oh, now we receive a new person? Well, this also breaks because now our main package is not using the good one. So now we're tying both of these changes at the same time, which is not something we want to do. Also, if we were printing p directly, we would see that while before it was working, so our old.person with old.person would print Francesc is 34. When we migrated to new, and also this one to new, which is already a problem, the fact that we're tying two different packages to change at the same time, that is a big problem. We also broke this. So it turns out that this is not what we want to do. We want to keep all of the methods. So maybe we should do a struct that is an old person in order to then print the good thing, but now age is not there anymore because this is actually now an old person inside. So now we're using both types, which makes it everything even worse. So this is actually not a good way of moving something from A to B, which is a big issue. So, okay. So how can we fix it? Well, type aliases. By using a simple type alias, now everything works. Why? Well, because even though we're defining a new person, that new person is exactly the same type as old person. So even if utils.go expects an old or a new person, we don't care. Everything will still work because they're exactly the same type. There are different names for one single type. So everything will just work. Okay, so then we can go here and be like, okay, so now we're going to use new in this one. Utils, we're going to use new. Still compiles. And then we're going to simply move this out of here into here. So we moved it from old to new. And now everything works. And we're done with the refactoring. This is something that before would have been incredibly hard. Actually, not incredibly hard, but simply impossible to do in this way. Cool. So have you seen any place where this has happened before? Okay, so to finish with the episode, I'm going to show a specific piece of code where type aliases made it way easier to migrate from an old package to a new package. And this for the context package. Now, the context package was added to the standard library with Go 1.7, but before that, it existed as a different place, golang.org/x/net/context. And there's a lot of people that had to migrate from the old code to the new code. And before Go 1.9, that was actually quite painful. So let's write an example where we show this. Now, in order to use previous to Go 1.9, I'm going to be doing Docker. I'm going to be using Docker to be able to run the function, right? So if we print the runtime.version, if we run this, this should print, that is wrong, runtime.version, and that's a function. It will print go 1.8.3. So I'm using Docker for that to make things easier. Otherwise, I need to install two different versions of Go. Okay, so let's imagine that we have a function that says hello, given a context. Why not? And it simply prints hello. Okay, and then we have a context with background, context background, and we call hello. Everybody's happy, everything works, good. Now, what we're going to do next is we're going to say, cool, we want to migrate from the old one. Actually, let's start from the old one. Okay, so from the old one, this doesn't work anymore because I need to get the thing. Okay, so now if I run it, it works. I just had to go get the golang.org/x/net/context in order to have it inside of the Docker image. Cool, so now let's try to migrate little by little. So actually there's not that much, right? So what I'm gonna do is I'm going to call this all context, and this will be all context and all context. And I'm also going to get the new one, context. And let's say that I'm going to migrate first this part, context.background. Well, this still works. There's no problem because now we're trying to use a new context as an old context, but the value of the old context satisfies the new interface, and the other way around because it's exactly the same interface. So we're good with this. What if we did it the other way? Context here. Well, everything works. No problem with that either. Cool. So where's the problem? Well, the problem is a little bit more subtle. What if we had a function that said do, that given a function that receives a context, and also context calls f with context. So we have this now, and let's all use the all context for everything for now. Okay, so this still works, and because it doesn't do much, but we can do context hello, and that will print hello still. So do calls f, which is hello, passing the context that we gave it. So everything works here. Let's see what happens if we start here using the new context. Nothing, no problem. But now, if we try to use the new context here, this will not compile. Because now we're trying to use this function that receives a context interface, a new context, as a function that receives the all context. And even though those two interfaces are equal and identical, they are not the same type. So two functions that receive one and the other do not have the same type. And that is a big problem. And somehow, if we run this in Go 1.9, main.go, this works. How did they do this? How is it possible that in Go 1.8, this code does not work, and it is therefore impossible if do and hello were defined in different packages, in different repos? This would require an atomic change, which is something we want to avoid. How is it possible that it's done with a new one? And it's actually really cool, because what we've done is that for pre-Go 1.9, the type context is a new interface, right? That happens to have exactly the same methods and everything as the as the other interface, but it is different type. In Go 1.9, the type context is an alias, and the type cancel func is also an alias, which means that now both types, even though they're defined in different places, since they're aliases, they're exactly the same. So if you're building something, if you're building this with Go 1.9, even if you're doing an import of golang.org/x/net/context, the type you're using at the end is the one from the standard library, because we're able to do an alias. And this is amazing. And this is why I think the type aliases is a solution for a very specific problem, yes, but an important one that many people have faced when they start having big code bases and changes over time of interfaces or functions, specifically those types that we think will never change. Maybe they not change, but they move from a package to another, and that causes huge problems. And with this, with type aliases, those problems should be smaller or inexistent. Or at least that's what I hope. Well, and with that, we reached the end of the episode. I hope you enjoyed it. It's a very different one. I had to actually write a script for this one, an actual real script. I had to think more about the examples to make sure that everything made sense. This is actually the second time I record this episode because I didn't like that much the previous version. And this is also why it will be released later on Monday rather than early in the morning. But I hope you don't mind. I hope you enjoyed the episode. Let me know if you did or not. You can leave comments or find me on Twitter as Francesc. Also, you can send me ideas and feedback to forum.justforfunc.com. And as always, thanks so much for watching, and see you all in 2 weeks.